Hi, welcome to Redox Reactions Part 7. My name is Dr. English, and today we're going to be talking about electrochemical cells, specifically voltaic cells. So today we're going to look at what is electrochemistry, specifically what is a voltaic cell, the components of a voltaic cell, half cells, electrodes, looking at a specific voltaic cell that utilizes zinc and copper, the function of the wire, and finally the function of the salt bridge. So what is electrochemistry? Electrochemistry is the study of two processes. One where chemical energy is converted into electrical energy, and the other being where electrical energy is converted into chemical energy. Two distinct types of electrochemical cells involve chemical reactions and a flow of electrons. Today we're specifically going to be talking about voltaic cells. In the next video we're going to be talking about electrolytic cells. We have an example of a potato clock right here, which is a chemical reaction producing electrical energy, and we've seen this before in the front of my classroom. So what is a voltaic cell? A voltaic cell is a type of electrochemical cell in which a spontaneous chemical reaction produces a flow of electrons, otherwise known as an electric current. So now you might ask, well, what is a spontaneous reaction? A spontaneous reaction is a reaction where no outside sources affect the reaction. It's going to occur on its own without any type of intervention. Voltaic cells are a specific type of electrochemical cell that produces electricity harnessed from the spontaneous reaction. You might also hear voltaic cells be referred to as galvanic cells. An example of a spontaneous reaction would be the reactions that we've been talking about lately, which are single replacement reactions. Below we have one type of single replacement reaction, where we have zinc, which is a more active metal than our copper, which is involved in this copper 2 sulfate solution. The zinc can come in and kick out the copper. The copper precipitates out to form solid copper metal, and the zinc becomes part of the solution. This is an example of a spontaneous reaction, and more specifically, a single replacement reaction. Now let's briefly look at the components of a voltaic cell before we get into more detail. To create a basic voltaic cell, the following parts are needed. 2 half cells, which we're going to represent here by these beakers, so these are our half cells. 2 electrodes, we're going to see these as most likely pieces of metal. Other things can be used, but we're going to focus on metals being our electrodes. A wire, which is going to be represented right here, and a salt bridge, which is going to connect the 2 beakers, aka half cells, together. You could also have a voltmeter attached to your wire up here, and that would help monitor how much electricity in volts that's produced. Now let's talk specifically about the half cells. A voltaic cell consists of 2 parts called half cells, in which the separate oxidation reduction reactions take place. In each half cell, a metal electrode and an ionic aqueous solution with a common metallic ion is present. Now you might say, Dr. English, why do you need a common metallic ion? Well, if I was to throw an active metal into a solution with a less active metal, I'd be having a spontaneous redox reaction right in my half cell, and that would be not good for producing electricity. So I want to make sure that my metal electrode and the metal that is in solution are the same. The reaction that takes place in each half cell is called a half reaction, which should sound very familiar to you. So 2 reactions will always be taking place in a voltaic cell. An oxidation half reaction in one half cell, and a reduction half reaction in another half cell, which we've basically been talking about with redox reactions. You cannot have one without the other. Oxidation always accompanies reduction, and that's going to be the same thing here in this voltaic cell. Now let's talk more specifically about the electrodes. Electrodes are 2 surfaces, typically metals, but not always, that can conduct electricity. Now this is really important right here, hugely important. The electrode where oxidation is going to take place is called the anode, and the anode has a negative charge associated with it. This electrode will always be the more reactive metal, the more active metal found on table J. The anode has a negative sign associated with it because electrons originate from this electrode. So again, one more time, key things that you need to know. Oxidation occurs at the anode. The anode is negatively charged. The anode will also be the more active metal out of the two electrodes that you're going to be using. Now, the other important thing is that the electrode where reduction takes place is the cathode, and the cathode has a positive charge associated with it. This electrode is the less active metal found on table J. The cathode has a positive sign associated with it because electrons are consumed at this electrode. Over where oxidation is taking place, electrons are produced, and where reduction is taking place, electrons are consumed. Very important to know the difference between the anode and the cathode, and that the anode is where oxidation takes place and the cathode is where reduction takes place. A memory device that might help you remember this is Red Cat and An-Ox, where oxidation occurs at the anode. So An-Ox, see, look, it's a little ox. Ooh, An-Ox. And then Red Cat, where reduction occurs at the cathode. Another way to remember anode and cathode, and actually the one that I prefer, is that oxidation and anode both start with vowels. Cathode and reduction both start with consonants. That's the way I like to keep them straight. It's up to you, whatever you'd like to choose to help you remember. So let's apply our knowledge to a voltaic cell using zinc and copper, going along with the general theme of the cell that we've been looking at so far. The following redox reaction can be separated into two half cells where two half reactions will occur. Solid zinc metal and copper 2 sulfate produces zinc sulfate and copper metal. We can take this single replacement reaction and split it into two half cells to basically harness the electricity that can be produced from this chemical reaction. So again, in one half cell we're going to have our zinc electrode and our zinc sulfate solution. Our zinc electrode right here is going to undergo oxidation. So zinc, and then it says from the zinc rod. The zinc is going to undergo oxidation and become zinc plus 2 and produce 2 electrons. At the same time, we have the copper electrode, which is known as the cathode because that's the less active metal. We have our copper 2 sulfate solution. Now, it's not the copper electrode that's going to get reduced here. Instead, it's actually the Cu plus 2 ions from the solution that's going to gain electrons and become solid copper. So copper metal will actually be plating or depositing itself on this copper electrode in this cell. If you were to take your finger at the very beginning of this reaction, before the copper metal is put into the copper 2 sulfate solution, if you were to take your finger, the copper electrode would feel very, very smooth. Once you put this voltaic cell together and you let it run for a while, and afterwards if you picked up the electrode and you ran your finger over it again, the electrode would actually feel bumpy because these copper 2 ions that are in solution are actually getting pulled out, they're gaining electrons, and they're forming solid copper metal. So we can see how this original chemical reaction up here can be split into two half reactions, with each half reaction occurring in one of the half cells. Let's look specifically at the zinc half cell. The first half reaction involves solid zinc being oxidized. So here's my solid zinc right here. This is my electrode. Electrode. When this undergoes oxidation, it's going to form zinc plus 2 ions and release 2 electrons. So the construction of a zinc half cell, we need a strip of zinc metal in a beaker of aqueous zinc sulfate solution. So we can see right here, we have our zinc from the rod, our zinc ions, and our 2 electrons, and we can see this little red arrow right here is pointing to the zinc plus 2 ions going into solution. And already in this solution, we have Zn plus 2 ions that already exist. So this whole reaction just ends up producing even more Zn plus 2 ions. In the copper half cell, this is going to involve aqueous copper ions being reduced because remember, in this half cell, we have copper 2 sulfate solution, which means there is a bunch of Cu plus 2 ions hanging out in here, floating around, Cu plus 2. So these Cu plus 2 ions will pick up 2 electrons and become solid copper metal. So this is solid. That's what the little s represents, solid metal. So what do we need to have to construct a copper half cell? We need a strip of copper metal and a beaker of aqueous copper 2 sulfate solution. Now remember, just like before when I say to you, okay, what's being oxidized, what's being reduced, only the reactants are either undergoing oxidation or reduction. So when I look at my half reaction right here, it's the Cu plus 2 from the solution that's being reduced, and that's really important to remember. Now, what's the purpose of this wire? Neither half cell can produce electricity on its own. They must be connected together. This is done by connecting the 2 metal electrodes together with a wire to allow electrons to flow from the anode to the cathode. And that's why in all of these representations of our voltaic cell, we've seen our little wire represented right here. Here's our wire. And they show the electrons going, the electrons represented by these little e's, and the electrons are pointing from the anode to the cathode. So as the zinc electrode undergoes oxidation, it's going to form zinc plus 2 ions, and then the 2 electrons actually go into this wire. They get pulled up and they travel through this wire from the anode over into the cathode and then go in right here to the electrode right here. The anode has a negative charge associated with it because we know that our electrons are negatively charged, and this is where they're originating from. The copper electrode is going to have a positive charge associated with it because this is where the electrons are going to be consumed. Now you might say, well, do I have to remember that the electrons always travel from the anode to the cathode? And I would say, yes, yes you do. So you think A, B, C. Okay, follow your alphabet, always from the anode to the cathode. By following your alphabet, you will be able to track where the electrons originate from and where they're going to. So what do we know about this reaction? Solid zinc is more active than solid copper according to Table J. The solid zinc, the electrode, is oxidized when the electrodes are connected and the spontaneous reaction occurs. It's actually pretty cool. This zinc electrode over time will actually start to deteriorate and fall apart as the solid zinc becomes zinc ions, and it basically, falls apart. The solid copper, again, is not reduced. It's not reduced. It's Cu0. It can't gain any more electrons. It's not going to happen. Solid copper is a product of the redox reaction. Instead, it's the positive copper plus 2 ions in the aqueous copper 2 sulfate solution that are being reduced to solid copper and plating on the surface of the electrode. This is really important. Again, the electrons originate from the solid zinc, our anode, flow through the wire to the solid copper cathode. The buildup of negative electrons in the solid copper will attract the copper plus 2 ions in the aqueous copper 2 sulfate solution towards the charged copper electrode. So this electrode right here, as all the electrons enter it, will suddenly have like this coating of negatively charged particle, negatively charged electrons. And here's Cu plus 2 thinking, hey, I'm positive, you're negative. I'm going to gain you, become solid copper, yeah, get reduced. So the Cu plus 2 is attracted to the electrode, picks up the electrons, and becomes solid copper right here. So the Cu plus 2 ions will plate themselves, actually form a solid, on the solid copper electrode and gain the electrons to be reduced. And we see this in this half reaction right here. But we have this tiny little issue, little problem. In the oxidation half cell, we're going to have a buildup of oxidized Zn plus 2 ions. Here's the zinc. Here's the zinc electrode. Great, it's being oxidized. I'm producing zinc plus 2. The zinc plus 2 ions are flowing into the solution. That's great. Zn plus 2, plus 2. Zn plus 2, Zn plus 2. Oh no, there's a lot of Zn plus 2 right here. The zinc ions are a byproduct of this oxidation reaction. There are now more Zn+2 ions in the aqueous solution than there are sulfate ions, which are our spectators. So guess what? This whole thing, really, really positive. Lots and lots of positive ions. So the solution is becoming very positively charged. This is called a problem. Same thing is occurring in the second half cell. All the Cu+2 ions are being pulled out of the aqueous solution, leaving only sulfate ions behind, because these Cu+2 ions, which are originally in the solution, are coming over to the electrode, picking up electrons and being reduced to solid copper. So what's left in the half cell? Well, a whole bunch of sulfate ions, SO4-2, SO4-2, and there's nothing really to balance out the charge of these SO4-2 ions. So these sulfate ions are just spectator ions. The solution is becoming very negatively charged. So we have one half cell that's really positively charged and one half cell that's really negatively charged. A large difference in charge will halt the redox reaction unless the half cells can be neutralized. And this is where our salt bridge is going to come in. The salt bridge. A salt bridge consists of a tube containing a non-reactive aqueous ionic solutions such as sodium nitrate. Now think about sodium nitrate for a minute. Sodium is a group 1 metal. Very, very soluble, not going to react with anything. The nitrate ion, NO3-1, also very soluble, not going to form a solid with anything. This is a great thing to have in our salt bridge. Salt bridges are very, very important. The function of a salt bridge is to connect the two solutions of the half cells together to allow ions to move from one half cell to another without fully mixing the two solutions. So positive ions can travel, negative ions can travel, but it's not like we're taking the two half cells and dumping them together. We are not doing that. So we can see here again that sodium nitrate can be broken down into sodium ions and nitrate ions, and when needed, the positive and negative ions in the salt bridge can move around and help neutralize the two half cells. In the first half cell, if an excess of Zn+2 ion builds up, which it will happen as this oxidation half reaction occurs, the nitrate ions from the salt bridge can flow in and neutralize this excess positive charge. So coming out of this salt bridge right here, it's like, hello, I'm nitrate, NO3-1, you're Zn+2. So the nitrate ions can basically come in and neutralize whatever positive charge is here. Or another way is that the Zn+2 ions can actually flow, let's change our color here, they can actually flow into the salt bridge, get pulled out, and also help with neutralizing the half cell. So the excess of Zn+2 ions can enter into the salt bridge and be neutralized by either existing nitrate ions or the excess sulfate ions from the second half cell. In the second half cell, if an excess of sulfate ions builds up, the sodium ions from the salt bridge can flow in and again help to neutralize the excess negative charge. Or the excess sulfate ions can enter into the salt bridge, go right here. And here we have this red arrow saying, hello, this sulfate ion is basically going into the salt bridge and being neutralized by existing sodium ions or the excess zinc ions from the other half cell. By neutralizing the charge, the voltaic cell is able to run longer. So to summarize, in a voltaic cell, chemical energy is converted to electrical energy. The anode is the site of oxidation. The cathode is the site of reduction. Electrons will always flow through the wire from the anode to the cathode. Voltaic cells are spontaneous. The anode has a negative sign associated with it, and the cathode has a positive sign associated with it. So what did we learn? Well, we went over the concept of what is electrochemistry. We talked about what is a voltaic cell. We looked briefly at the components of a voltaic cell. We talked in more depth about half cells and electrodes. We looked at a specific type of voltaic cell that used zinc and copper as its electrodes. We looked at the function of a wire, and finally the function of the salt bridge. Need more help? Feel free to contact me. Have a great day.